today we complete this effective field theory treatment. The basic idea is the effective field theory shifts the focus to the infrared. The unknown high energy theory is just parameterized by a few constants. In the infrared, we were looking at non-analytic stuff, which in position space is non-local. So we're interested in that. You could get out predictions that are independent of the high energy theory. So these are low energy theorems of quantum gravity. They're most often small, but this is the content of GR, of quantum GR. So the place where we left off was we were doing the Weinberg theorem, Weinberg's infrared gravitons. So what I'd like to do is an example of that. We saw that he showed that there is cancellation of infrared divergences. There's a neat example of this, which is just graviton-graviton scattering. Okay, the scattering amplitude involves diagrams that look like this. So there's the quart of 4 graviton vertex. Maybe I should make these things squiggles. Looks like that. There's pole diagrams that look like this, plus pole diagrams that look like this, plus pole diagrams that, if this is 3, 4, we come out with 4, 3. So it's symmetry. And I showed you how terrible those vertices look like. And the 4 graviton one is even worse. Here's where the miracle occurs. And so if I gave that as a homework problem, you'd be there for a long time. But the miracle occurs is that there's only one amplitude left when you do this. If you on shell, you do plus, plus. So here's momentum coming in this way. The S channel is that way. S is going to be P1 plus P2. P is P1 minus P3. This is squared. U is P1 minus P4 squared. And so if I'm coming in with a given helicity, lambda 1, lambda 2, and going to final state helicity, the only one that survives is plus plus goes to plus plus, or so it's plus 2, or minus 2 goes to minus 2, minus 2. Okay, so that's what the amplitude is. It's the only thing you need to know there. It's I, it's this kappa squared over 4. And you think it'd be some big awful mess. It's not. It's S cubed over TU. So this is something that makes you think that there's something simpler to do than just write out those Simon rules. The actual amplitude simplifies very much. This is a dimensionless amplitude, so just because I'm going to count powers here. If you think of S, it goes like energy squared, T and U go like energy squared. This is of order G energy squared, which is then dimensionless. Okay, that's actually typical of scattering of 4 bosons. or dimensionless amplitudes. If you remembered, when we did the pion scattering, it was the pi one was T over V squared. It was the momentum transfer divided by V squared. That's the same pattern here. Okay, so it looks just like that. Okay, then to do one loop. So,
John, I have a question for.
Yes.
What do you mean by plus plus to plus plus? Is that just the first diagram?
So this is the helicity of the one incoming guy is +2. The helicity of the other incoming guy is +2 also.
Okay.
Okay? And you preserve the helicity as you go through the scattering process. Okay? That answer it?
Yes.
Okay. So one loop. Well, you can start drawing diagrams here. Basically you take diagrams like you have and you start squaring them. So there's diagrams like this, but then diagrams like this guy too. But then pole diagrams, you could have things that go like this. I don't know. It starts, and then there's box diagrams. Remember, I showed you the box diagram, how painful that is. Okay. So there's an enormous number of diagrams involved here. This was actually first done. Actually, tree level even was not done early on in the game either. It was, it took up to about 1960 or so before somebody finally wrote that out, maybe 70. But this was done by Dunbar and Norwich. And what they actually did is it was strings-based methods. So when you do string theory, your world sheet summarizes a whole bunch of Feynman diagrams. But then they can pick out the pure gravity part. The zero slope limit of gravity, closed strings, pure gravity. Okay. But in the end, the answer shows a set of interesting features. So let's see, here's results. Okay, so first let's just do power counting on this thing. This is, so there's kappa to the fourth s squared. That's also dimensionless. So this, remember, the first order was, this is order g squared, well, g e squared squared. So we do, it's next order in the energy expansion. Sorry. So that is as expected. The one that has existed at lowest order now picks up things that look like logs. Let's just, so here's the tree amplitude. That's the one that I wrote above. Then it's STU divided by ST. So there's the extra power of energy squared with logs. So you get your logs. You also got some term that didn't have logs. One of the things to point out is there's no C1, C2 here either. So this doesn't depend on these coefficients at all. And there's a reason for this. This is, remember, pure gravity was one loop finite. So there were no divergences here, and you sort of knew this ahead of time. And that, remember, followed because we could, the graviton satisfy R mu nu equals 0 and R squared equals to 0. So the C1 and C2 terms, the terms in the Lagrangian, disappear when you take matrix elements of them. So, in fact, there is no there was no need for renormalization here. It's a nice finite result. However, if your eyes are good, and not everyone's eyes are good here, I can tell. If those sitting 2 rows back don't see it. Here's a but 1 over epsilon. So what's going on there? Okay, this is a dimensionally regularized amplitude. 1 over epsilon. You can forget these gammas 1 minus epsilon. Those are all at best finite corrections because you've got this 1 over epsilon here. Otherwise, you could take epsilon to 0. Okay, so what's going on? But this is in fact what Weinberg has talked about. This is in infrared divergences. Not a UV divergence. So infrared divergences that comes, it's present in box diagrams in particular. So if you draw a box diagram with massless particles, there's a box that has infrared divergences. So do even diagrams like that. Okay, that's a typical one. So that's another one of the diagrams I could have drawn up there. And this has actually been checked. It cancels with the radiative process, the radiation. It was checked by my student Torma. And so you basically add the lowest order diagram, the one loop corrections, and the radiation, the soft radiation. And you find that all the 1 over epsilons disappear. And it's replaced by some function of the resolution, the energy resolution of differentiating from delta E, differentiating whether you've radiated or not. So it works just like Bremsstrahlung. Okay, so this is the Weinberg theorem in action.
John?
Yes?
Is that soft radiation detectable in principle, or is it a technical?
No, so typically the story with soft radiation is that if it's too soft, your detector can't detect it, but there's always a threshold where your detector could identify the radiation. And your answer here in the sum of these depends on the resolution of your detector and tends to depend on it logarithmically. So that's what's buried in that silly function there. So in principle, yes, you could detect it. And if you go off and look at decays into charged particles that are done with high precision, then you can actually see this effect. You can, an example that I know well is K goes to pi plus pi minus gamma. People can measure that the spectrum of the gamma down to some energy, and it has this log behavior, and then it merges at some stage with just k goes to pi pi, because your detector can no longer tell soft gammas. Okay, does that answer the question? You okay with that?
Yes.
Okay, good. So the point is it does behave just like normal infrared radiation. But the other thing that I found interesting about this process is this lack of UV divergences. Yet another low energy theorem. No matter what the high energy content of quantum gravity is, that's what graviton-graviton scatter looks like. The next example is another one that illustrates some of the features of it. This is work that I did with Barry on Reissner-Nordstrom metric. So the Reissner-Nordstrom is the gravitational field around a charged object. And there's some full solution here, but let me just give you the Taylor expansion because that's what we do. So it's 1 minus 2 gm over r. That's the usual gravitational piece. There's then a g alpha over r squared correction, and then there's a whole nonlinear completion of this, and gij is delta ij minus g 2gm over r delta ij. That's what we saw before. Then there's a g alpha r ij over r squared okay. Minus delta ij, thank you. This is actually written in a particular gauge. This is harmonic gauge, which we're going to work in anyhow. And okay, and then the calculation, which I'll do, let me just fill it in here. It's not that I care so much about the answer here, but let's just show you what it looks like. It looks like 8/3 g over pi alpha h bar over mr cubed, and this guy is plus 4/3 g over pi alpha h bar mr cubed ri rj over r squared minus delta ij. Okay, so these are the quantum pieces. And I should say that I've taken alpha to be q squared over 4 pi. There's no h bar in this guy. Okay, so it's not over h bar. I don't know where my c's go. But that, by making that choice, it allows h bar counting, because here's the classical piece with no h bars, and here's a piece with h bar. Okay. Okay. one of the things you see here is that this correction here is the same order as the classical pieces, and that's because gravity is classical here. And I'm doing photon loops. So the types of things I'm doing are diagrams that look like that. So this is a photon coupled up to graviton H. Or let's just do some more of them. Well, there's a diagram that looks like this. Gamma, gamma, H. There's diagrams that look like that. There's diagrams that look like that, etc. So the nice thing about this is that it's just QED really. It's photons coupled up to charged particles. But this actually is the reason I want to talk about it, is it makes us easy to see what's going on. So here, since gravity is classical, we basically have box h mu nu is minus 16 pi g t mu nu minus 1/2 eta mu nu t lambda lambda. So I've done weak field gravity, and then this lets me invert. I have then minus 16 pi g integral d3q 2 pi cubed e to the I q dot r 1 over q squared and t mu nu of q minus 1/2 eta mu nu t lambda lambda of q. Actually, I skipped one step in here. This basically says h is integral d4y or d3y. Actually, I just some Green's function x minus y t of y. But then I just Fourier transform that whole bloody mess, and I get the usual 1 over q squared. So basically, all I have to do is take a matrix element. Okay, and then here's the matrix element. So if I want p prime t mu nu of x p, that has e to the I p prime minus p dot x square root of 2e prime. There's normalization factors. There's 2 p mu p nu times some f1 of q squared plus q mu q nu minus g mu nu eta mu nu q squared f2 of q squared. Here, P, capital P, is P plus P prime over 2. Q is P prime minus P. And these F's are form factors. Okay, so this is the general expansion constrained by Lorentz invariance. And the calculation just basically goes as before. Calculation comes the following. Basically, you're just calculating these form factors. F1 of q squared, I won't give them both, I'll just give one of them, is 1 plus alpha over 4 pi, q squared over m squared, some number which I didn't bother copying down, plus 3/4 m pi squared over the square root of q squared plus 2 log minus q squared over m squared. Okay, so the point is to again point out that you get this non-analytic pieces, you get the square roots. This gives me the classical correction. This gives me the quantum piece. And you reproduce, by this calculation, you reproduce the GM over R, the G alpha, and the G alpha H bar terms. The G alpha over R squared comes, it's basically just plugging this form up into here and going back. This guy comes uniquely from the following diagram. Comes from this diagram there, gamma, gamma. This guy comes from a bunch of diagrams. It comes from that guy. Also things like that one also plays a role. Okay. But for me, this is just standard effective field theory technology at this stage. For me, the big fun about this one was the interpretation of the classical piece. Okay, if you take, let's look at position space for the moment. And I take T mu nu at R is integral d3q over 2 pi cubed e to the I q dot R T mu nu of q, where this is what I just wrote up there. That's you take these two pieces there and you Fourier transform. So I'm just Fourier transforming this guy, and it's just 3D Fourier transform, and you find T00. Well, the one piece, the piece that starts off here, T00 is just in the non-relativistic limit. These guys cancel, it's just a constant. You get, T00 is M delta 3 of R. Okay, not surprising. And then you get plus alpha over 8 pi R to the 4th, and then minus alpha H bar over pi M R to the 5th. Tij is, there's no delta function piece, it's just minus alpha over 4 pi R squared Ri Rj over R squared minus 1/2 delta Ij with alpha over 3 pi H bar M R to the 5th delta Ij. Fourth, thank you, Barry. R to the 4th it is. He knows the interpretation is coming up. The interpretation is to recall the classical E and M. The energy momentum tensor for E and M is minus F mu nu, F mu lambda, F lambda nu plus 1/4 eta mu nu F lambda sigma F lambda sigma. If we are looking around the charged object, we have the electric field is Q over 4 pi r squared r hat, and T00 is then 1/2 E squared. That's of course what you knew. Is then alpha over 8 pi r to the 4th. Tij is minus EI EJ plus 1/2 delta IJ E squared equals minus alpha over 4 pi r to the 4th Ri Rj over r squared minus 1/2 delta IJ. And if you compare them, you see that the classical pieces up here exactly equal the classical pieces there. And so what we've learned is that this Feynman diagram has measured the E squared around the charged particle. Okay, so this then tells us something about this, how you get classical physics out. How else would you have got the E squared that existed as energy around the charged particle within the Feynman diagram approach, except for that guy? So it's part of explaining why you get the result that you get. So any questions about that stuff? I like that. I found it neat. Okay, next example, I won't do in too much detail, but let's just talk about it. Bending of light. At one loop. Okay, so this is a recent paper that Barry and I again have written with Bjorn Bohr, Peter van Hove. And us, and one of Pierre's students. So basically, in a Feynman diagram approach, you're taking photons, you're scattering them off some heavy guy like that, and you're doing this at one loop. So there's a bunch of diagrams. Oh, the diagrams can be crazy. You can have gravitons here, so those double lines are the gravitons. But there's also things where the photon comes down and the graviton goes across that way. There's a lot of these. Now this is an adventure driven by Bjorn Bohr and Van Hove, where we use some new calculational methods, which I had hoped to talk to you about, maybe will, but okay, first part of it is that instead of calculating all the Feynman diagrams, you just reconstruct the amplitude from the unitarity cuts. So this is a whole set of methods based on unitarity. So in one of these pictures up here, for example, the cut would be you calculate photon scattering, and then photons interacting with an extra graviton there. Those are both simpler calculations, and you can reconstruct the amplitudes from that. And so basically what you have to do is you have to calculate, here's a photon coming along, here's a big blob, here are two guys coming out, they can be photons or gravitons, here's another big blob, and here's the heavy particle. And so these are either gammas or gravitons. And you calculate that cut, and you use the fact that all these amplitudes are either bubbles, boxes, or triangles. This is the Passerino-Veltman. So Passerino-Veltman tells us that all one-loop amplitudes can be decomposed into factors times the scalar box, the scalar bubble, and the scalar triangle. And we know the cuts associated with those, and so you are looking at calculating the cuts. And then there were some other tricks involved. There's this gravity is the square of a gauge theory has been useful. Again, maybe we'll talk about it at the end. But anyhow, that's a whole set of new methods. But that's not exactly what I want to focus on. I don't have time for that here, but let's just look at some of the results. Okay. So the results, the matrix element, this is the helicity conserving matrix element. So in the language we used before, be +1 goes to +1. It has the mass of the heavy guy. I'm taking the non-relativistic limit for the heavy guy. The energy of the photon, that's squared. There's a kappa squared out in front. There's a 1 over T. T, you can, this is, comes from this diagram there, the 1 over T. And then you get 1. Well, there's a kappa squared m over square root of minus T factor with the number is 15 over 512. Again, by our logic that we've done before, this should be a classical correction. There's no H bars floating around there. Then there's a kappa squared H bar. Here's one with an H bar. The same coefficient, 15 over 512 pi squared log minus T over m squared. But then there's another log. So this one, the one that comes with m squared, has the same coefficient. The next log is kappa squared. Oh, I'm sorry. There's a factor of T there. Kappa squared T over 64 pi squared log minus T over mu squared. And this guy actually has a coefficient out here, which I'll just call B sub I. And B sub I is minus 161 over 120 for a photon. And if I had a massless scalar, B sub I is 3 over 40. Okay, and we're not quite done yet. There's also a plus a kappa squared T over 128 pi squared with a factor of 3 log squared. And we're not done yet. There's one more. There's kappa squared m omega I log minus T over m squared. All right. So, interesting features here are that, well, let's first deal with this guy. When I told you about Weinberg's infrared photon paper, I said there was a Coulomb phase and a Newton phase. This is the Newton phase. Presumably that exponentiates, but we've certainly not worked beyond leading order. This was enough. But one of the things you see is that it doesn't have the same kappa squared T dependence that the others do. It actually has this M omega piece. It looks almost classical. So that factors out. Of course, when you take an amplitude, it drops out. There's a new log squared. This is new. And this gives you actually is going to give infrared divergences. When you integrate it, the regular logs are okay. This guy doesn't. Okay, and then there's a little extra magic in this paper. So there's the amplitude. So it has a new piece. The numbers here are interesting. The numbers are different. So they're different for different particles, different for gammas versus scalars. That's interesting. There's a new infrared piece, and then a phase. Okay. Mu is actually mu is the scale parameter that you do when you do dimensional regularization. This is going to disappear into infrared factors. Okay. You'll see the final result has some infrared factor. Okay, so there's the amplitude. Now, what we ended up doing next was something semi-classical. We put this into a semi-classical potential. And, well, I'm just going to give you the answer. Basically, you get, so the bending angle was 4gm over b. B is an impact parameter. Then the next piece is the 15 over 4 g squared m squared pi over b squared. Here's the post-Newtonian correction. And interesting, that comes out right. That's from this classical piece up here. The classical piece did the classical physics. And then there's a bunch of terms which, all right, I'll just write it out. 8b sub I plus 9 is 48 log b over 2r0 over pi g squared h bar m over b cubed. So there's your quantum piece. The interesting features for me are, so R0 is some infrared cutoff. I don't think we treated that very well, frankly. That comes from this log squared. So basically one of the logs turns into this log and the other log Fourier transforms into the 1 over b cubed. So I don't think we did a good treatment of that yet. We're coming back to and trying to do better on that. But there are some interesting features here. One is that this violates the equivalence principle. This violation is tiny, but it's still there. It's basically the photons, massless photons and massless scalars bend differently. Things don't move on geodesics anymore. Okay. And this is actually understandable within the calculation. And basically, the classical motion, you have this metric in the background. You just follow the metric when you're going around the sun. You're just doing a geodesic motion. But when you're doing the quantum corrections, let me exaggerate. There's occasions where you're emitting, let's say, a graviton. That graviton's propagating a long distance. It's coming back, and then you're interacting with the sun. But you're not local anymore. You're not at the same point. You're not at the point where the classical geodesic would have followed. You're at some different point. So this is some non-local effect. I tend to call it tidal effects. Tidal effects are ones where the object has a big spatial extent, but you can't remove this. So if you were doing a big object moving around the sun, you would just say, well, the equivalence principle holds in the limit where that's a test particle of infinitesimal size. But here you can't have infinitesimal size anymore because your object is inherently quantum and inherently spreads out. So I think this motion not being geodesic, violating the equivalence principle, is a generic quantum feature that should be expected.
Are there soft gravitons?
So the soft gravitons, that's what I'm complaining about my own calculation for. We didn't do the Bremsstrahlung correction because we were doing this semi-classical treatment. We just put a cutoff in there. Presumably that would be cut off by soft graviton emission. But we haven't done this by doing the usual quantum mechanical way of squaring, forming a cross-section, doing something like that. It turns out if you just form a cross-section and follow your nose, you don't get the right behavior. You don't even get the right post-Newtonian behavior. And it's easy to prove that that's wrong, even though there's people in literature who have done it. It works at leading order, but everything else doesn't work. So We were just emailing this morning about how to try to get better than this. So what one normally does, the calculations that are in the literature involve forming a cross-section, then making the identification of the cross-section to the classical amplitudes by the usual classical mechanics, d sigma d omega is b dB type of thing, to the impact parameter, and then just identifying that. And you find that if you do that for a 1 over r squared potential, or 1 over r potential, you get the right answer. If you do it for any other potential, you get the wrong answer, both classic, in comparing quantum mechanics and classically. Okay, and so it's, people have gotten this first term out by doing that, but you don't get the second term correctly. Okay, and it's not actually a right identification beyond leading order. Okay. All right. Other things that I wanted to say here. Anyone have any questions on that? Okay, is there a question? I wanted to briefly talk about running coupling constants in gravity. Or more precisely, the lack of running coupling. Just quickly, the running couplings is one of the great ideas of field theory. So if I'm doing QED, let me just do this pretty quickly. If I do QED and I do photon exchange plus the vacuum polarization diagram plus etc., sum up those, that turns into E squared. Well, let me circumvent this step. Is just 1 minus pi hat of Q squared, where I've already renormalized this, and pi hat of Q squared is the vacuum polarization function minus pi of 0. Okay. It's actually equal to E squared over 12 pi squared log minus Q squared over mu squared when Q squared is bigger than the masses involved. Okay. And one can take this function and define a running coupling constant that depends on Q squared, and being slightly fancier, one defines the beta functions, etc. So let me not say much more about that. That's something I hope that everybody has seen here. The basic point is that gravity doesn't behave that way. Okay, and it partially does, because in fact we saw when we did the following type of calculations. We did calculations like that, and calculations with gravitons running around, and these all have a universal form. There's some momentum factors, p, momentum 1 over epsilon plus, well, let's make this q plus log of Q squared over mu squared. Okay, So there is a log that sits there. And when we define C1 and C2, we actually have to define them at some renormalization point. This would be the bare ones, C2. And let me not bother with the C2, but let's do, it's 1 over 9. That's plus 1 over 960 pi squared 1 over epsilon minus gamma plus log 4 pi plus log the renormalization point squared over mu squared. Okay, and there's this one has something similar. We don't need to do that, but it basically when I renormalize, I get C1 and C2 that depend on the scale that I renormalize it. So this is scale dependent. Okay. So those like the running of the electric charge, logarithmic running. But G doesn't have this feature. Okay. So if I do, let's go back and do something like this. Here's vacuum polarization diagrams plus a bunch of other ones. So what we saw when we did this is we saw that this started off as G over Q squared plus G squared. Well, we had, let's just do this guy right here. There's a 1 over Q squared there. The loop went like Q to the 4th. There's a 1 over Q squared there. And we ended up with terms that look like A plus B log Q squared. So there's a log there. But if I look at this, and it's G over Q squared plus G squared A plus B log Q squared. Well, the attempt might be to say, why not define G of Q squared as G 1 plus G Q squared A plus B log Q squared. Okay, some collection like that. So why not? There's a type of a running coupling constant that you could maybe get behind. Okay. Well, there are some problems with it. So let's do problems. Well, one is that there's a ambiguity because Q squared can be greater than 0 or Q squared can be less than 0. So if I was doing the process that I did here with some running coupling constant, here's Q squared is less than 0. If I cross that over, this is Q squared greater than 0. So is G of Q squared increasing or decreasing? Okay, well, you could maybe get around that. Maybe you don't care about whether it's increasing or decreasing. the you could maybe, if there was if it was still useful, you could maybe do a function that both increases and decreases depending on where it is. However, there's the second problem I think is bigger. There's a lack of universality. Okay. So one of the reasons why photons are useful this way is every time you have a photon exchange, you have vacuum polarization. So every time you have it, it's the same function. It's independent of what those external states are. That's not the case here. There's two parts of this. So one would be, which diagrams do you do? For example, when we did the vacuum polarization, we did this diagram and showed that in some units that was plus 43 over 3 over 5. But so you might want to do that. But then other diagrams had the same contributions, the same. You couldn't factor it out. So this plus this gave me plus 94 over 3. So that's quite different. If I did, it was this diagram here was plus 45 in the same units, and this diagram here was minus 56 in the same units. So normally in running coupling constants, you don't include these, but if you didn't include them, you'd get totally the wrong answer. If you include some subset, you get random answers. So there's no good definition that falls out of that. That also could be maybe gotten around. Maybe if there was if you could figure out something universal, you say, well, this guy's universal and that one's not. You could do it. But the real killer is that different processes have extremely different results. So remember, we saw two heavy guys. I have all those interactions were G over Q squared, 1 minus 41 over 41 over 20 pi, G Q squared log Q squared. And the thing we just did with light, you do all these diagrams here. This was G over Q squared 1 plus well, I've got copied down here 32 pi G Q squared. It was 15 over 5, 12 pi squared minus this BI over 16 pi squared log Q squared. And there was also a log squared piece, G Q squared over 4 pi log squared Q squared. So these guys have nothing to do with each other. There's no useful way that you get the common result from these processes. And the diagnosis, there's an easy diagnosis. If you know effective field theory, is power counting. Remember, loops have an extra power of GE squared each time you do it. We've seen that. And so they loop processes don't renormalize G. They renormalize instead new operators, C1, C2. There were some D1s, D2s for vertex corrections, etc., like that. These guys, there's many of them. They are process dependent. We could have put up Graviton-graviton scattering up here too. It also has nothing related. Whereas in QED, the loops renormalize E squared. And so you're dealing with corrections to the same particle. So power counting says that you shouldn't expect a running coupling constants here. I just have to finish here with this caution though. Caution is there's a lot of wrong papers in the literature. They're all over the place. And here's what they always do. They say, well, let's, instead of doing dimensional regularization like I'm doing, let's use a cutoff lambda. And then if you do a cutoff lambda, you always get G lambda, which is G 1 plus some constant times G lambda squared. And then they try to say the beta function of G, so beta for G is lambda dg d lambda, etc. It's not 0 then. And that's wrong. This is just wrong. Here's the feature. So this disappears in renormalization. Okay, so if you do this, you do, let's do some process. You do this plus this guy. You find that you end up with, let's put G0, 1 plus constant G0 lambda squared over Q squared. Okay, so you do get this correction. You get a correction to G that depends on lambda squared. But then you go out and you measure it. The coefficient of 1 over Q squared in the scattering amplitude is just G Newton over Q squared. G Newton is a fixed number. And lambda disappears. So G of lambda just turns into, so G0 of lambda just turns into the G Newton renormalized. Okay, so you just, this is just the renormalization of general relativity with a cutoff. If you then look at the next order terms don't have any running coupling constant, and you don't get it. So there's just too many papers out there that have that. Okay. It didn't get quite as far as I wanted, but we're almost at the end. I just had one more example to do, and then limits of the effective theory, and then we're going to